In the mid-20th century, Meyerhof observed a critical gap in existing knowledge. The overburden wasn't just a weight sitting on a surface. It was a complex system of confinement. While earlier models treated the soil above the foundation base as a simple surcharge, Meyerhof's 1951 breakthrough recognized that the shear failure surface actually propagates upward into the soil above the foundation level. This fundamental shift allowed for a much more sophisticated understanding of how deep foundations actually interact with the earth. At the heart of Meyerhof's contribution are the three dimensionless bearing capacity factors, NC, NQ, and N-gamma. These aren't just arbitrary constants, they are mathematical representations of how a soil's internal angle of friction, phi, resists failure. Meyerhof derived these by analyzing the geometry of the plastic equilibrium zones within the soil. In his model, these factors act as multipliers that scale the three primary components of resistance: cohesion, surcharge, and the self-weight of the soil, to provide a comprehensive picture of the ultimate bearing capacity, Qu. The factor NQ is arguably the cornerstone of Meyerhof's work, representing the resistance generated by the soil's surcharge. Meyerhof defined NQ using the formula e to the power of pi tangent phi tangent squared 45 plus phi over 2, which accounts for the soil's ability to lock together under pressure. From NQ, he derived NC, the factor for cohesion, through the relationship NQ minus 1 cot phi. This elegant link ensures that as the friction angle increases, the contribution of the soil's cohesive stickiness is appropriately scaled, reflecting the reality that these two properties work in tandem to prevent shear failure. Perhaps the most debated and researched of the three is N-gamma, which represents the resistance provided by the weight of the soil within the failure wedge itself. Meyerhof's derivation, NQ minus 1, tangent 1.4 phi, was a departure from previous theories, providing values that generally fall between those of Terzaghi and later researchers like Vesic. Because N-gamma increases exponentially with the friction angle, it becomes the dominant factor for granular soils like dense sands, where the self-weight of the rotating soil mass provides the bulk of the foundation's support. What made Meyerhof's factors revolutionary was his assumption of a rough base for the footing and his analysis of the varying shapes of the failure wedge. He recognized that as a foundation is pushed into the ground, a triangular wedge of soil moves down with it, pushing adjacent zones into a state of plastic failure. By calculating how much energy it takes to displace these zones, while accounting for the friction along the soil foundation interface, Meyerhof provided engineers with a way to calculate the stability of structures that weren't just sitting on the surface, but were embedded deep into the stratigraphy. Ultimately, Meyerhof's work transformed geotechnical engineering from a series of conservative guesses into a rigorous analytical discipline. His N factors remain the most widely cited and utilized in the field because they strike a balance between theoretical precision and practical reliability. When we look at a table of NC, NQ, and N-gamma today, we aren't just looking at numbers. We are looking at the refined geometry of the Earth's resistance, a legacy of George Meyerhof's quest to understand exactly how the ground holds our world together.